Hey folks, time to do some walkthrough instruction corrections on our B-level instruction. This is basically how to calculate speed from a position time graph and how to interpret curves on a position time graph. So this is the assignment that you are working on. Just a quick reminder of what the notes told you. To figure out the average speed from a position time graph, you've basically got to calculate its slope, which is its change in y values over its change in x values, also known as rise over run. So the rise tells you how much the position changed, the run tells you how much the time changed, which works really well into our average velocity equation, which is distance over time, y over x. Another quick reminder is what the curves tell you on position time graphs. So if we're looking here, same as straight lines, if the curve is going up and to the right, you are moving in a positive direction, or up or to the right. If you are going down and to the right, so as time goes on, the graph is moving down, that's a object moving in the negative direction, so moving left or moving down or backwards. Up and to the right, it is moving in a positive direction. Down and to the right, you are moving in a negative direction. If the curve is becoming steeper as time goes on, that means it's speeding up. Again, here we're still going steeper as time goes on, so it's moving in the negative direction on this graph, but it's still speeding up. If it's becoming shallower over time, it is slowing down. Okay, let's take a look at the first question here. Here's hoping I get it right the first time, because I only printed one copy and now I'm working off site. So section A, is it moving right, left, or stopped? Well, we can see that it's moving up and to the right, so we are going right. B is right. I'm going to start just using letters. C is still going to the right. D, that is a horizontal line, so it is stopped. E is going down to the right, so it is a object moving left. F is down to the right, left. G, horizontal, stopped. H, down to the right, is going left. I, down to the right, left. J, down to the right, left. K, now we've turned around, we are now going up to the right, so that is in the right direction. L is going up and to the right, so it is going right. Section A is becoming steeper over time, so it is speeding up. So speeding up. B is a straight line, so that is a steady speed. C, that's becoming shallower over time, so that is slowing down. Oops. Okay. D, since it's not moving, I would say that that is a steady speed of 0. E is getting steeper, so it's speeding up. F, becoming more shallow, so it's slowing. G is flat, so a steady speed of 0 again. H is becoming more steep, so it is speeding up. I is a straight line, so that tells us it's a constant speed or a steady speed. We're on to J now, becoming more shallow, so therefore it is slowing. K, becoming more steep, so it is speeding up. and L is a straight line. Since it's a straight line, it is steady. Perfect. Let you look at that for a second, then we're going to go on to question number 2. Make sure we're still in the frame. Awesome. Vector the physics bear is out meandering around town looking for the nearest McDonald's because he is having a major Big Mac attack. Can relate. He walks along the street searching. He starts at his house but never finds the McDonald's. Oh, unfortunate. The graph below shows his position over a period of time. So we see him searching, still searching, stopping for a bit, turning around disappointed. So let's draw the motion on the number line below. Remember this from earlier. So let's pick the points where his speed changes. So we're going to pick this point, this point, this point, and this point. So we know at time 8 seconds, he was at 25 meters. So 25 meters, he was there at 8 seconds. Next one, we know that at 24 seconds, he was at positive 35. So positive 35, he was there at 24 seconds. He was still at 35 meters at, in between 32 and 40, that should be 36. So he's there at 36 seconds as well. He was heading that direction. He stayed there. And then from 36 seconds until 52 seconds, at 52 seconds, he was back at 0. So 52 seconds. He went back this direction. Now I guess the only thing I really left out there, bit of an oops on my part, at time 0, he was at 0 meters, which was his house. So let's just add that in right now. So at 0 seconds, I'm really sorry, that's hard to see, he was at 0 meters. From there, he went to the right in 8 seconds to 25 meters. Awesome. So why did Vector never find McDonald's? Well, let's take a look at the number line we gave you. If you take a look, he was always moving in the positive direction, but this tells you here that the McDonald's was to the left of the house or in the negative direction. So it's because he went in the wrong direction. Last thing we have to do on this page here is find Vector's average speed from 0 to 8 seconds, from 8 to 24 seconds. 0 to 8 seconds, 8 to 24 seconds, 24 to 36 seconds, and 36 to 52 seconds. So we've got to figure out what his rise over his run was. Oh, I shouldn't change this orientation. Good. So speed equals distance over time. We can see here that the distance traveled in between 0 and 25 meters is a total of 25 meters. So this portion here is 25 meters. 25 meters over from 0 to 8 seconds is 8 seconds. And then we're going to do a little bit of fancy math here. Didn't plan ahead, but I've got my phone, so I've got a calculator. We can do 25 divided by 8 to give ourselves 3.125 or 3.13 meters per second. Okay, 8 seconds to 24 seconds is this section here. We can already predict that it's going to be a lower number because the graph is less steep. So let's take a look here. We still know that we have speed equal to distance over time. from the graph itself, we can draw ourselves this fancy little triangle. If he started at 25 meters and ended at 35 meters, it means that he changed his position by 10 meters. It's going to be 10 meters traveled. If he started at 8 seconds, traveled until 24 seconds, that's a total of 16 seconds. And if we do our 10 divided by 16, we get 0.63 meters per second. Awesome. Okay. Now, we're going to do the math here, but you should have an idea of what the speed's going to be during this section. Because it's a horizontal line, it means that they had no change in position, which means that their speed was going to be 0. But we can prove that using math. Speed equals distance over time. If you started at 35 meters, ended at 35 meters, that means you traveled 0 meters. If you started at 24 seconds, ended at, what time? 36 seconds, it means that we had a change in time of 12 seconds. If you don't believe me, put it into your calculator. 0 divided by 12 is a big old 0. 0 meters per second. And finally, 36 seconds to 52 seconds. Notice here, we're moving in the negative direction. Now, we can even keep that in mind when we're doing our speed. And I'll show you what it tells you. So speed equals distance over time. If you started at 35 meters and you went all the way to 0 meters, it means that your distance changed, or your position changed, by 35 meters. But it's actually negative 35 meters. If we look at our time change, we went from 36 seconds to 52 seconds, which is a change in 16 seconds. And if we do our math here, 35, which was a negative, divided by 16 will give us negative 2.19 meters per second. That negative just tells you that they're traveling 2.19 meters per second to the left. Positive numbers would mean you're going to the right, negative would mean you're going to the left. Excellent. The rest of the questions in this booklet use very much the same skills. I will post them all in the answer key. If you guys need any run-throughs besides the ones that I showed, please ask. We can arrange something to give you a little bit more instruction. Thanks, folks.